Hello everyone. In this video, I discuss the integrals of various inverse trigonometric forms. So previously we learned that the derivative of sine inverse x is 1 over square root of 1 minus x square. And if we reverse this formula, we get the integral of 1 over 1 square root of 1 minus x squared dx is equal to sine inverse x plus c. And similarly, we also learned that the derivative of tangent inverse x is 1 over 1 plus x square, and the corresponding integral formula is given here. But what if we have something like this? So in place of 1, we have a. So square integral of 1 over square root of a square minus x square dx is sine inverse x over a. Since we know that substitution method is like reversing the chain rule, so you can think of what would be the derivative of sine inverse x over a. So derivative of this would be 1 over square root of 1 minus square of the angle. So angle in this case is x over a. So x square over a square times, by chain rule we also need to take the derivative of x over a, which would be 1 over a. And if you just do some algebraic manipulation, you will see that you get a over a square minus x square 1 over a. So in this case, a and a cancels and you're left with 1 over square root of a square minus x square, and we get the corresponding integral formula. Similarly, you can derive the formula for integral of 1 over a square plus x square, and this is your inverse tangent form. So 1 over a tangent inverse x over a plus c. Notice that here we don't have a square root in the denominator, so that's why we have one extra 1 over a which was left over. So take a good look at these two forms. We're going to use these in the coming examples. Let's take a look at the first example. So we have to evaluate the integral of 1 over x squared plus 6x plus 13 from -1 to 3. So if we look for the first time in this problem, so it seems like it doesn't fit in any of the categories that we have discussed so far. However, if we try to write denominator in a new way, we can see that it fits one of these forms. You can think of x squared plus 6x plus 13, the denominator as, so let's just rewrite this as 6x plus, so 9 plus 4. So I chose 9 here so that I can make a perfect square, because I know that the first three terms will give me a perfect square, and then the last term is 2 square. So now we have this form where we have a constant square plus a variable square, so which fits with our this form. So it means we can evaluate this integral. So here it was easy to complete the square, but sometimes it's not as intuitive. So in that case, you can you can follow the proper procedure. So if you want to find the perfect square, so if you want to complete the square of any quadratic expression, you can always set that equal to x plus a whole square plus b. And now our goal is to find the value of a and b. For that, first we expand x plus a whole square, so that would be x square plus 2ax plus a square plus b. So in this case, we see that we have two quadratic expressions that are equal. So we equate the coefficients of like terms. So equating Equating the coefficients of terms containing x, we see that 6 equals to 2a. So from here, a should be 3. So equating the constant terms, we find that 13 should be equal to a square plus b. And we already found the value of a. So it means 13 is equal to 3 square plus b. So b is 13 minus 9, which is 4. So it means we can rewrite this as x square x square plus 6x plus 13 can be written as x plus 3 whole square plus 4, and then 4 can be written as 2 square. So if it is not intuitive, you can follow the proper procedure to complete your squares. So now we have this form: variable square plus a constant square. So 1 over variable square plus a constant square, and we need the differential of variable. So in this case, our variable is not x, it's x plus 3 here. So we need the differential of x plus 3 on the top. So let's see if we have that. So let's say u is equal to x plus 3. So our variable is u, and the differential of the variable would be dx. So we have the variable square plus constant square, and we have the differential of variable on the top. So it means we can use this formula here. So using this result, we get 1 over a. So a is 2 in this case. So we get 1 over 2, and we get tangent inverse. And in place of x, we have new variable, which is x plus 3. So x plus 3 over a, which is our 2 plus c. But since this is a definite integral, so we're gonna plug in our limits from -1 to 3. So putting the upper limit, we get 3 plus 3 over 2, so which is 6 over 2. So tangent inverse 3 minus, so -1 plus 3, so 2 over 2. So tangent inverse 1. So after solving this, we get about 0.2318. So we can see that the use of completing the square uh, uh, so helps us to solve the integral of quadratic expressions. Let's do some more practice with one more example. So this one we can start by separating this into two different integrals. So we're going to write this integral as sum of two integrals. So now let's analyze these two integrals separately. So if we take a look at the first one, so in first one, we don't have 1 on the top. So we have 2r. So we have some variable on the top and some variable expression in the bottom. And we notice that, so this is of the form. So if you consider your fx as r square plus 9, and the differential of that would be 2r dr. So we notice that this is a logarithmic form. So let me remind you, the logarithmic form is if you have reciprocal of a function, so 1 over fx, and then you have differential of the function along with it. So then the derivative is ln of absolute value of the function plus constant. So using that, we can see that for the first integral, we have the logarithmic form. So the answer should be ln of r square plus 9 plus c. So I'm just going to write the constant only once. For the second part, we notice that we have this form 1 over x square plus a square, or a square plus x square. And we know that this is for the tangent inverse function. So I'm just going to rewrite this as 5 times integral of 1 over r square plus 3 square dr. So in this case, our a is 3 and our x is r, because our variable is r. So what we get here is ln of mod of r square plus 9 plus 5, and then 1 over 3, so it means 5 over 3 tangent inverse r over 3 plus c. So this would be our solution. So it's very important that you recognize the correct form of the integrals. There is very subtle difference in each form, but you should be able to figure that out, that what form stands for what formula. So in the next video I'll discuss few cases where we will find out, or we will compare the different forms. So I'll explain how to find what formula or what form to apply.